Okay, so to perform this integral, what are we going to do? Well, we will change we'll change coordinates. So we will change to three angles and the magnitude of this vector KE, okay? And that's just because the integrand doesn't depend on the angles. So what does the integral become? Well, it becomes minus I. We will have an integral over these three angles. So I'll write this as d omega 3. We'll have an integral over the radial variable, the magnitude of KE. And now what's the measure? Well, when we look at d4KE, so look at this expression over here, d4KE is a product of 4 powers of the momentum. So that's the dimension that the measure must have, 4 powers of the momentum. Here, d omega 3, well, that's purely for the angles, so that's dimensionless. So the measure has to be dk multiplied by k cubed. This is just like in 2 dimensions, dx dy is r dr d theta. That r dr is length squared, the d theta is dimensionless. And it's just like in 3 dimensions where dx dy dz becomes, what is it? R squared dr sine theta d theta d phi. Sine theta d theta d phi is dimensionless, but r squared dr is length cubed. dk times k cubed is momentum to the power of 4. Good. And then for the integrand, what do we have? We just have k squared minus delta squared. The magnitude of the vector must be integrated from 0 to infinity. And these angles here at each k, each value for the magnitude k, we are integrating over a 3-sphere. So that's the integral that we want to do. Now, where does the divergence appear? So the divergence is for large k values. Okay? And so what we can ask is, how does star behave for large k? Okay, so this will be something like, I don't care about the minus I, that's not related to the divergence. The integral over 3-sphere will just give me the volume of the 3-sphere, 2 pi squared. But if I look at the integral, so I'll have an integral dk, and let's imagine I'm integrating up to some very big momentum lambda. So lambda is a massive momentum. I've got k cubed. And then if k is, sorry, what k cubed? If k is becoming very, very large, k squared minus delta behaves just like k squared, okay? Above some k, you won't even notice the minus delta. So we'll have over k squared squared, which is k to the power of 4. So this is how it behaves for very large k, okay? And integral dk of k cubed over k to the 4 goes like log of k, and we want to evaluate it at the upper limit lambda. So this is behaving like the log of lambda, okay? So this means star goes to infinity as lambda goes to infinity. And how does it go? Well, star will behave like the log of lambda. And of course, the log of lambda that does go to infinity as lambda goes to infinity. This is a big momentum divergence. So big momentum divergence. And the way that we say that, as we already discussed, this is a UV divergence. In fact, our language is slightly more specific. We would say there is a log UV divergence. Okay, so that's how we would describe this. If you had gotten an answer that looked like lambda, you would say there was a linear UV divergence. If you had got something that went like lambda squared, you would call it a quadratic UV divergence. It also could go like lambda cubed, the cubic UV divergence. If it went like 1 or lambda minus 1 or something like that, you would say it is convergent. Okay, good. So we're now getting infinity for the value of this integral. Well, we have to know how to proceed, how to define it. So how do we make sense of this divergence? And now, in fact, we have a new idea, and a new idea deserves a new color. So how to make sense of this divergence? We regularize the theory. And what it means when we regularize the theory, it means we change the theory. Change the theory so that there is no divergence. Okay, let me illustrate to you how we could do this. Okay, well, one thing that we could do is we could say, don't let the spatial momenta, so remember that K mu was K naught and K. Let's say, don't let the spatial momenta get too large. So we'll say K dot K can be less than or equal to lambda squared. This is called a momentum cutoff regularization. Okay, so this is one thing that you could do. And when you use this cutoff, then you see when you do your integral, you don't run all the way up to infinity. You run off to some finite value lambda, and you never let lambda tend to infinity. But as you take lambda to infinity, you recover the original theory. So, you know, you don't really have just one theory anymore. You've got a whole bunch of theories. You've got a different theory for each value of lambda. Now, what's the use of regularizing the infinity? You haven't gotten rid of it. So you're going to have to take lambda to infinity at the end of the day. So what's the use of doing this? Well, here's the idea. We regularize the theory. So work with lambda in place. Once you've got lambda in place, all of your matching conditions, your renormalization conditions are perfectly well defined. There are no infinities. Apply those matching conditions to express everything in the theory in terms of your physical mass and your physical coupling. Once you've done that, you can let lambda tend to infinity and you will have no divergences left in your theory. So the idea is you regularize your theory to make everything finite and well-defined, and then you apply your matching conditions, apply your normalization procedure, express everything in terms of the physical mass and the physical coupling, and once you've done that, you can lift the cutoff and go back to your original theory. So this whole process is called regularizing the theory. We change or deform the theory, and there's a way of letting that deformation disappear. So like lambda goes to infinity, we go back to the original theory. Now notice something. With this regularization that we're using, where we're cutting off the momentum, we have spoiled Lorentz invariance, okay? And why is that the case? Well, imagine you've got some momentum. I'll boost to another frame. Now the momentum gets slightly bigger. I'll boost again. The momentum will get bigger still. Well, I'll keep boosting, but there'll be a point at which the next boost will take me past the value of k dot k equal to lambda squared. So there'll be a boost that will push my momentum outside of the range allowed by the cutoff. So not every boost can be performed. There are some boosts that I'm no longer allowed to apply. So obviously the theory is not Lorentz invariant. Another way to see it, that cutoff equation, which I've outlined in the red box, well, that's not a Lorentz invariant equation. So if I have some values of the momenta, some Lorentz observers will say k dot k is below the cutoff squared, but there's some inertial observers that will already think that k dot k is above the cutoff squared. So we've spoiled Lorentz invariance. Okay, that's not good. Also, we have introduced a new scale, lambda. Lambda is got the dimensions of inverse length. If we've set h bar equal to c equal to 1, so that's a new scale that we've introduced into the theory. And it's not a good idea to just introduce all sorts of new scales. Okay, but this is not the only way to regularize the theory. In fact, there are many ways to regularize theories, and many different ways were considered. So we need some sort of a way to think about these different ways of regularizing the theory, so that we've got a way to think about regularization in general. Well, there's a very old paper by Rosen and Landau, and in that they come to the conclusion that regularization must always spoil some features of the theory, some symmetries of the theory. So we know we're going to spoil symmetries. So one way of comparing different regularization schemes is to ask what symmetries they break. Okay? And a good regularization scheme is the one that breaks as few symmetries as possible. And from this point of view, there is one regularization scheme that is probably better than all others. And that is called dimensional regularization. So dimensional regularization. Dimensional regularization was invented by 't Hooft and Veltman. And this certainly is at least part of the reason why they won the Nobel Prize. The nice thing about dimensional regularization is that it preserves gauge symmetry. If you're dealing with scalar fields, it preserves Lorentz symmetry. It preserves just about everything. Of course, it has to break something, and it breaks scale symmetry. But what we'll see later on is that this breaking of scaling symmetry is even something that you can measure. So in some sense, it's physical. That's a prediction of quantum field theory and not an artifact of our calculation, our regularization. So what's the idea? Well, we start in 4 space-time dimensions. And then the way that we deform the theory, we change to working in d space-time dimensions. And 't Hooft and Veltman wanted to define the theory in d dimensions, where d can be any complex number. Okay, so not only, so you're used to thinking of an integer number of dimensions. So 't Hooft and Veltman say, no, you don't have to be in 4 dimensions. You could be in 3.99 dimensions or 1,5 dimensions. Even more than that, they say you could be in 2 plus I dimensions. So you could even be in a complex number of dimensions. And what we will find is, if you calculate quantities in d dimensions, in general, they are finite, well-defined numbers. So our integrals will converge nicely. But when we set d is equal to 4, the infinities will reappear. So we are going to define our theory in d dimensions, do our renormalization, so use our renormalization conditions. Once we've expressed everything in terms of the physical mass and the physical coupling, then we'll be able to come back to 4 dimensions, d is equal to 4 dimensions, and the infinities won't give us any problems. The only symmetry that we will spoil is that we will spoil scale invariance. Now, if your particle had a mass, well, you didn't have scale invariance to begin with. So maybe a better way to say this, instead of saying we spoil scale invariance, you can also express this as we introduce a new scale. And you'll see exactly where that new scale comes from. Okay, so next we want to develop dimensional regularization, and we'll do that in a moment.